Welcome friends to my channel. Now in my previous lecture I shall discuss about T and ds equation. Now in this video I shall discuss the variation of internal energy with volume. Okay, so I shall discuss about the variation of internal energy with volume. Okay, by using Maxwell's thermodynamical relations. Okay, so what we write from Maxwell's relation, we use this relation, this del S del V temperature constant, this is equals to del P del T volume constant. So you multiply it both sides by T, so T del S del V temperature constant, this is equals to T del P del T volume constant, and TdS is nothing but dq, so T del S means del q, so we can write this, so this is equals to this. Okay, again from first law we can write del q, this is equals to del u plus P del V. So we substitute this here, this del u plus P del V by del V T, this is equals to T into del P del T volume constant. So what we can write? We can write del U del V temperature constant plus P, this is equals to T del P del T volume constant. We write this, so from this expression we can write del U del V temperature constant, this is equals to T del P del T volume constant minus P. So this equation represents the variation of internal energy with volume. Okay, so this is the general equation that represents the variation of internal energy with volume. Okay, now let us discuss the various cases that we find. Okay, let us discuss the various cases, special cases, what happens in case of gases or solids or liquids. Okay, so first of all you take ideal gas. First of all you take ideal gas. Okay, so what happens in case of the ideal gas, that is PV, this equals to RT, 1 mole ideal gas. We can write PV, this is equals to RT. So what happens if we differentiate this expression with respect to T, keeping volume constant, that becomes R. So from this expression we can get del P del T volume constant, this equals to R by V. So we get it. So if we substitute this value here, so what we get, del U del V temperature constant, this equals to T into del P del T volume constant means R by V minus P. So RT by V mean RT by V means P, so P minus P will be 0. So you can see for a perfect gas there is no variation of internal energy with volume. So from which we can easily conclude that internal energy of a perfect gas is a function of temperature only, because if there is a temperature term here, then the partial derivative with respect to V will be 0. So if U involves T, then with respect to V, the partial derivative is 0. So we can clearly say for a perfect gas, there is no variation of internal energy with volume, that is U is only a function of temperature. Okay, so this you all know, and if you are asked to show that why or how U is depend upon T. That is, if you are asked that internal energy is a function of temperature only, show it, then you can do also this. Okay. So for a perfect gas, there is no variation of internal energy with volume. So U is a function of temperature only. Let us check what happens in case of a ideal gas. Okay. So let us check what happens in case of a real gas. Okay. So what happens in case of a real gas? So what happens for a real gas? We all know for 1 mole real gas we can write the van der Waal equation. This. Okay. The van der Waal equation. So if you differentiate it with respect to T keeping V constant, then this term is totally constant. So you can write it, and you have to differentiate this. This is also constant because you are doing differentiation with respect to V. A and B both constant, so this is 0. So this we can write this. So from which we can write del P del T volume constant, this equals to R by V minus B. Okay, so what happens? Internal energy, variation of internal energy with volume, that is T into del P del T volume constant minus P. So this is simply RT by V minus B minus P. And what is RT by V minus V? This term P plus A by V square. P plus A by V square minus P. This cancels. So for real gas, the variation of internal energy with volume is not 0, and there is a value which is A by V square. Okay, so for real gas the picture is quite different. Okay, so we have taken perfect gas and we have also taken the real gas. So let us check what happens in case of solids or liquids. Okay, what happens in case of a solids and liquids. Okay, so what happens for solid and liquids? What happens? So in this case we all know that alpha, this is the volume expansion coefficient. Okay, that is increase in volume per unit rise in temperature. Okay, increase in volume per unit rise in temperature, volume expansion coefficient. Volume expansion coefficient, increase in volume per unit rise in temperature. Okay, so this is volume expansion coefficient, and you can write ET. This is also isothermal elasticity. This is the stress term, and this is del V by V. This is strain, volume strain. So you can write it isothermal elasticity. So if we multiply both the terms, then what we get? We get this. This is del P del V temperature constant. So what is del V del T? This is minus del S del V T. Del S del P T. So this is what? This is del S del V temperature constant, which again means del P del T volume constant. So for solids and liquids, this term can be represented as the product of alpha and ET. So what you can write? Del U del V T, this is equals to T into, we have del P del T volume constant minus P. So you can write T alpha ET minus P. So for solids and liquids, this term can be represented in following way. So there will be alpha. So the depends on alpha and isothermal elasticities. Okay. So in this lecture, I discuss about the variation of internal energy with volume, and we also discuss the different cases. Now in our next class I shall discuss about the heat capacity relations. Okay. So dear guys, if you don't subscribe my channel, then kindly subscribe it. to get latest updated videos. Okay, thank you.